Okay, welcome everyone to the deep dive.
Glad to be here.
Today we're getting into something maybe a bit unexpected. We're looking at how advanced math, specifically calculus, connects with something really down to earth.
Soil science, yeah. It's a fascinating link, and we've been looking at a source that really digs into this.
Exactly. It focuses on nutrient depletion rates in soil.
hmm How quickly those essential nutrients get used up.
So our mission today is basically to unpack that. How does calculus, and one idea in particular, help us understand this?
The derivative.
Right, the derivative. How does it show us how fast nutrients are disappearing? And, why is knowing that speed so important?
It's crucial, yeah, for managing land, for farming sustainably.
Okay, so let's jump in. Calculus. Soil. On the surface, maybe not an obvious pair.
Not immediately, perhaps. But this source makes a really strong case by focusing on rates of change, how things change over time.
Which is fundamental to calculus, right?
Exactly. And the source zeroes in on the derivative. So,
Yeah.
if you happen to be studying calculus, maybe differentiation right now, this is a perfect real-world application.
Ah, okay. So how does it use the derivative?
Well, it uses it to measure the instantaneous rate of change. So not just the average loss over a season, but how fast nutrients are being depleted at like any specific moment during a crop cycle.
Instantaneous rate. Okay, so like a speedometer for nutrient use. Not just the total distance traveled, but the speed right now.
That's a great way to put it, because nutrient use isn't always steady. The force shows it can speed up or slow down. Think about a plant's growth stages, soil moisture,
And
temperature.
lots of factors.
Exactly. And the derivative gives you that precise speed reading at any point. So the source uses this, for example, with nitrogen in cornfields. It shows the depletion rate really ramps up during a specific phase, the tasseling phase.
Oh, interesting.
Yeah, it depletes almost twice as fast then compared to earlier growth stages. And that specific insight, that comes directly from applying the derivative. That's the key takeaway here.
Wow. Okay, so knowing that specific speed, that rate at different times, why is that more useful than just measuring levels at the start and end? What's the big deal about the rate?
Well, that's where the practical value really comes in, which the source discusses. Knowing the rate allows for much smarter decisions. Think about sustainability.
How so?
The source looks at phosphorus depletion under different farming practices, like no-till versus conventional tillage. By analyzing the rate using derivatives, they found different patterns over the whole cycle.
Okay.
So maybe no-till starts slower, but the rate might change later. Understanding that dynamic helps decide which method is truly more sustainable for that nutrient in that soil long term. It's more nuanced than a simple before and after picture.
Got it. So it's about the how and when of the loss, not just the total.
Precisely. And that directly impacts planting fertilization too.
Right, that makes sense.
The source is clear on this. Knowing, say, that nitrogen uptake accelerates during corn tasseling lets farmers time their fertilizer applications. They can add it right when the crop needs it most and is drawing it down fastest.
So you avoid putting too much on early where it might just wash away.
Exactly. Or too little too late, which hurts the yield. You're matching the supply to the rate of demand. Calculus gives you the tool to gauge that demand rate accurately.
And I guess different crops, different nutrients, they'd all have unique depletion rate curves.
Oh, absolutely. The source mentions potassium for soybeans, for instance. Very different depletion curve than nitrogen in corn. The derivative is the mathematical tool that lets us measure and compare these distinct dynamic processes precisely.
That's really powerful. It takes a core math concept, differentiation, and shows how it gives us these really specific, actionable insights into natural systems.
Yeah, into processes we can't just easily see, like nutrients moving in the soil.
It really underlines how math helps us understand the world in a deeper way.
Definitely. It provides a language to describe these dynamic changes.
So here's something to think about as we wrap up. Where else in the world around you, maybe in nature, maybe elsewhere, is understanding the rate of change, that precise speed, not just the overall shift, really the key? Where else might the method, or learning unlock some surprising understanding?